And today we should go through the topic practical aspects of linear regression. So it should be a lot less theory, a lot more practical stuff. So the practical stuff is, maybe you already seen it in your exercises. If you are given some example of a distillation column where there are multiple things which are measured, like temperatures, pressures, sometimes some compositions, but that's not the rule. And you wanna find out, for example, our typical example is what is a composition of some distillate or bottom stream, because physical chemistry with the mandatory lectures is telling us that this should be somehow correlated. Yeah, there are all these equilibria which are telling, okay, if we have a mixture of two liquids at a given temperature, pressure, everything is in equilibrium. This temperature should indicate, for example, what is the composition. And the problem is that there is no lack of the measurements. There is abundance of the measurements. There is more measurements than actually we have possible data. Let's illustrate it. Of course, we are trying to work out our linear regression model. This is already in the prediction form, but the columns of this matrix X, well, can be, columns of X can be temperature at the first tray, temperature at the second tray, pressure at the top, pressure at the bottom, and so on, and so forth. We can also think about having like multiplications. I don't know if it would make sense. Probably this wouldn't make sense from the physical point of view. We can also think about some, I don't know, there is the standard distillate to feed ratio, how much product in the distillate we are getting, how much feed we are feeding in. And so there can be any type of nonlinear transformation of these data. Of course, any other things, e to the power of something, of some temperature. If you remember Arrhenius' law, that's quite common. And yeah, so the question is how to decide about these terms. Slightly, well, it's very similar, but slightly maybe less complicated version is if we are trying to build a model which is a polynomial. Yeah, so let's say we have some p0 and maybe only in one variable. We can do some polynomial expansion to basically whichever degree. Of course, this gets even more complicated if we, for example, would have two variables. Then we get some cross products, stuff like that. So again, and you might have already faced it. I remember your physical chemistry labs are usually stopping at some linear, well, this linear term, and maybe sometimes this quadratic term, then you can analyze by some means how well this or that polynomial would fit. So the question is how to go about this, how to select something reasonable. We already, what we have finished last time with was we studied this correlation concept. So now we can say whether it's this sort of data in the matrix X, or whether it's this sort of data, whether these independent variables would be correlated, and close to this correlation is the concept of dependence. Now comes the question, what does it mean if something is dependent, should be correlated, and if something is correlated, should be dependent? Yes or no? In other words, should we just write like this double-side implication? So if and only if something is correlated, then it is also dependent, and it's dependent, then it's correlated or not. What was the example that we were finishing?
Correlation doesn't mean that it's causality.
Mm-hmm. Yeah, we can also call this causality. Okay, so then the double-sided implication holds, or we should rewrite it in some way.
I would say it's not equivalent implication, like dependence is correlation, but the correlation isn't dependent.
And I deleted it the other way. Yes. Correct. So if there is a dependence among some variables, then we should see it in the correlation coefficient. It would imply correlation. Correlation doesn't imply that there is a dependence. If you recall our last example, the number of students at this faculty going abroad or coming from abroad, well, they were pretty much correlated, but this correlation was only caused by the COVID pandemics, which made all these numbers drop at the same time. So they were dropping at the same time, but it didn't mean that few less students coming to this faculty would imply that there is less students also coming out. Okay. So when we are talking about this correlation, when we spot some correlation among some independent variables, yeah. So if x1 and x2, whatever they are, temperatures, pressures, and so on, if they are correlated, that's actually an unwanted situation. Unwanted situation. Let's detail it next. But actually, for some whatever variable, let's say x1 and y, well, the correlation is actually welcome, right? Because, well, we are trying to make sense of a y based on the data x, yeah. So we would measure some x, let's say temperature, and we want to correlate it to some desired variable that we wanna predict. For example, composition. So there should be some correlation. Otherwise, this this parameter can have even completely random value, wouldn't correspond to the reality. So yes, here the correlation is desired. Let's try to plot this this unwanted situation. Let's say that we are building a model which has just two parameters, two inputs, two independent variables, and we didn't check for the correlation. We actually don't know. We actually don't know that our data x1 and x2 would look maybe like this. Yeah, we just disregard. We build our matrix X, and we go ahead. Maybe this already means that there is some hidden relationship. Let's say, I don't know, x1 is k times x2. This can be a natural phenomenon, like the two temperatures at the distillation column at the stages or trays which are close to each other. They would be very much correlated. Or it can be also a problem of experimentation. We are trying to build a correlation between some composition, temperature and pressure, and for some reason we decide, and this is not a arbitrary example, it happens many times, and for some reason we would just decide, well, okay, let's do several experiments, and whenever we increase the temperature, we will increase the pressure. Yeah, so these are our independent variables. We set up the experiment, temperature, pressure, and then we measure some dependent variable that we wanna find this sort of model for. Yeah, let's see what are the consequences. So we can just easily plug this relationship. We don't know, but we don't know about it always, but we can assume that it exists. If it exists, then what? Let's plug it like p1k times x2. Yeah, replacing the x1 variable, and we keep our x2. We can now grab the terms with x2 together, and this basically means, well, there is only one parameter that we should be looking for, and whatever parameters p1 and p2 we will actually estimate, they will be already correlated to go close to the true value of this bracket. The problem is that then this p1 and p2 can be completely arbitrary, because let's say in reality we should find that this is equal to 3. Yeah, let's say just for the example's sake that the k is equal to 1. So, well, what are the combinations of p1 plus p2 being equal to 3? What numbers p1 and p2 can take such that they are equal to 3?
All real numbers? All real numbers?
Yes, just some example. Something easy. 1 and 2.
1 and a half.
1.5 and what?
That's the same.
Not like this?
Okay.
Equal to 3. I just chose that such that we don't have always just ones and zeros, but also -5 and what do I need? 8 would work. So all these values of P1 and P2 can be a result of our regression, and well, if they should represent some physical values, quantities, parameters, it doesn't seem to be reasonable to have this additional degree of freedom. What we can also easily imagine this situation. Think about this. That's my attempt for a 3D plot. So we have x1, x1, x2, which, let's say, have this correlation. And now for each of these combinations, x1, x2, well, we will measure our dependent variable. So our y, our data, something maybe would look like, let's say, our. Now I'm hitting the limits of my 3D plotting. Let's just try something and hope it works out. So let's say that the real function, the ground truth that we don't know, that we try to learn from the data, looks like this plane. But now, if we take the measurements, well, these measurements for x1 and x2, we will measure at the first experiment the value of some composition y, then we continue. Then, well, also our experimental data would look like this. And our model is, well, P1 and P2 is basically some kind of a normal vector to this plane. So this is what we are trying to learn. But what's the problem with this? Can you sense any problematic point? Is it fixed, or is it possible to find just one plane that would share this line? There are multiple of them, right? We can basically, if we basically take this line as some axis of rotation, we can basically fit any sort of a model very easily. We wouldn't notice. Our regression would go as usual. Yeah, you can easily compare it with the example where our points are better distributed. So our points no longer follow a line, and now it's quite hard to wiggle this plane such that such that this plane, our model would go away from our data points. Here it's very easy around this axis of rotation. So that's the problematic part. So that's why this situation is unwanted. It's good to tackle this situation as soon as possible, building a covariance matrix, doing some correlations, and get rid of the variables that are correlated in the independent, and to have x1 and x2 as independent as possible. Okay. So let's now maybe go to this this very simple situation where we are just building a polynomial model, just one variable, and let's say the data we have measured would look like this. So that's our independent variable. This is first our data points. What would you suggest to be a model? What would be the order? What would be the complexity of the model to fit this data? Quadratic. Why do you say so? Because kinda turns. Okay. Any other? Linear can be also.
There's almost unlimited ways to describe it.
Unlimited?
Yeah.
Unlimited, I didn't hear the word.
Ways.
Ah.
Like we can use any order.
Exactly. Exactly. Yeah. So if we try the linear one, well, doesn't look very bad. No, it's might work out. The data even look like okay. They can be they can just the error of our prediction can follow close to normal distribution. So it seems that we just have a problem with the noisy sensor. Maybe if we see the quadratic fit, okay, well, maybe from this point up they are fine. Here something bad happened. Maybe our sensor even had a malfunction. We can do whatever way. So there was linear, quadratic. Now this is octic fit. So I took a 8-degree polynomial. Doesn't it look lovely? It's just passing almost through any data point. Yeah. Is that the correct one? What do you think? Okay, good observation. Good observation. That it might go bad if we try to extrapolate. Okay, so let's try to extrapolate. Let's try to extrapolate our linear model. So what happens here? From 0 to 1 was where we where the data that I was showing before. This is our linear model, and from the point 1 farther, we didn't adapt the model. We just observed the data and we extrapolated our model. It looks apparently bad, right? But it's not the end of the world. So first message is oops, too much zoomed in. Whoops, still. Do not extrapolate. And if this one is still good. So linear models can be extrapolated. This is already, I mean, too far. Yeah, we almost, our model has seen only data from this interval, and we are basically doubling the size of the interval. So if we just extrapolate it a bit, then we would still be okay-ish. But even a bit, what Patricia already very nicely observed, if our octic fit would just completely ignore. Of course, it tries to fit all the data points. It tries to actually fit all the noise. We don't want to fit the noise. We don't care about fitting the noise. We want to fit the information that is in the data, and it will just nicely escape. So what is the remedy? And you have already seen this in your exercises, is to well, of course, try to get the data in the full range of where the model should be valid, where you wanna use it, and because, well, what's the point here? Maybe I fitted the data for some normal operation, and then I just started to use the model, and in a small bit of time there was a change in the operation in the plant. Yeah, different oil came to the refinery. A different supplier of some chemical is delivering different sort of raw material, and immediately your boss tells you, well, your model is shit, it doesn't work. Yeah, so how to avoid this?
How do we know that we have to fit the data with the polynomial curve?
Oh, well, you don't know, but you can try it as one of the guesses. Why? Because you learned in the mathematics that there is this Taylor expansion, that basically any nonlinear function you can try to approximate with the polynomial, and polynomials basically are good approximators. Yeah, you can also do there are. But this is advanced concepts, like if you spot in your polynomial model certain where is it? If you spot in this model certain patterns, then you can try think about how nonlinear is the relationship that you are trying to predict, or maybe what is the shape of the function, whether it's exponential, whether it's logarithm. Yeah, but well, it's usually some good correlation if you, or some good practice if you don't really have an idea. Yeah, I mean, we are using here the examples of distillation column, for which we have the feeling, so that you have a feeling. But if you are just estimating, well, the price of the stock, of the price of the Bitcoin, it's quite hard to know all the inputs to know what is the physical reality behind. So also a good question would be, how do I know beforehand what is the region of validity of my model? Well, it's not always easy to know, but well, you are hoping for the best, and if the situation with the extrapolation that we saw above would occur, you can either retrain your model by again collecting the data and so on, or there are some other techniques which will just try to, based on the observed data points, like in the live situation when the model is already working and predicting, that could take the recent data points and try slightly push some parameters of the model. We will discuss that in some other lecture. And then the idea would be to kind of try to simulate the situation that we will start to use our model, that we put our model to be live and doing the predictions, by having a sort of so-called validation data. So the idea is I have several experiments and I split the data to the training and validation. The training data would be used for calculating the values of the parameters, and validation data would be used to check whether the value of whether the prediction error is still okay, whether it is at least similar to what the training data would suggest. We'll get back to this. Let's just try to write it down. Let's say we have a this technique is actually has a name which is called cross validation. So in the cross validation we split the data into training data, validation data, and testing. TS. The idea is that we have the whole pool of our data points, and we do the split. We will keep some of the data, typically something like 20%, but it varies for the testing. This will be the data that we sort of put in the black box in a vault before we start to do anything with the rest of the data before starting to train the model. They will be used just for the final assessment. They are the final stamp. Like if I start to use my model in the daily production of a factory, then this will be the performance. The rest of the data will be split again, I don't know, 50 to 30 between the training and validation. How will this work? Let's say that well, we will be now choosing different models, either different orders of the polynomial, linear, quadratic, or we can also bring more and more terms, temperature at the first ray, temperature at the fifth ray, and so on and so forth. So basically we will be getting more and more complex models. Let's denote it with this number of parameters, MP. Yeah, because each of these will have in its own parameter. And well, what would happen with the? Let's put them, give them some colors. Training data, validation, and maybe testing. So what would happen for our training data? Well, this is the situation with the first doing linear fit, then quadratic, then cubic, and so on until the octic fit. Let's say we see we are observing some performance of the model. Let's say it will be the root mean squared of the prediction error. Well, what was the training yellow one? Well, what we can typically observe for the training data, the more terms we add, well, our model is based on optimization. It tries to please us. It tries to minimize the prediction error. So even though the reality, maybe our best possible model has just complexity of 3 parameters, well, we won't have a chance seeing in the training data what happens. Yeah, this is the situation where was that was our great octic fit. Yeah, if we would calculate the RMSE and compare with here, well, this one will be definitely much higher, because the octic model is just fitting the noise. So if we have the testing data at our hand, of course we would see a different trend. So of course the fit won't be as good, but maybe we would be able to see this badness of the octic fit or of some more complex model. So we would observe that there is some best order of the model, best complexity of the model at this point. And basically the whole idea is that we of course don't have the testing data. We put them in the black box, but we can simulate this testing data with the validation data that basically should go in a similar way. Why would why would we just playing with the? Why would we just keep the validation data? It's because, well, they are part of the data that we can use for whatever decision about the order of the model. Good. Does it make sense? Did also Rastio explain it somehow this way or intuitively this way during the exercises? Okay, first question. Does it make sense? I guess you witnessed all this already at your exercises. Of course, when we are talking about this RMSE, there are some other assessment criteria. So let's maybe go through them. Our assessment criteria. Of course, you already know this because you've seen it in your exercises. Root mean squared error. So RMSE, or root mean squared prediction error. Yeah. Sometimes there is even this P pronounced. How do we calculate it? Anybody recalls? Mean is here. We can start from here. Root mean squared error. It's very how to say it, like a very nomen omen, not definition, but the name. So we first need the root. So it's square root. Then we take the mean. So 1 over n sum from 1 to n. And what are we summing? We are summing squares and squares of the error. So we have a square, and our prediction error is the difference between what we measured and what we predict. Yeah, it's very easy. If you remember just RMSE, you can make it up. Okay, that's the first one, and very popular one. I also like, and probably you will recall it, and it's very much used, so-called coefficient of determination. Don't even recall the Slovak name. Where is my determination? But you will probably recognize if I say this is the famous R squared. You remember seeing R squared when you were trying to in some lab, when you were trying to say, oh, I did this fit. There was some standard deviation of a prediction error, something like RMSE. And usually also the R squared value was trying to indicate something. Do you recall by any chance basically how it works? Usually you are just given the formula.
It's like the exact fit, like it's perfect, and with 0 it's like it doesn't make sense at all.
Yeah. What does it tries to determine? This coefficient is it tries to determine whether the model that you built is better than just doing a simple fit, let's say by a constant. Let's draw it. Let's say that this is how my data looks. Just copy this. Copy. What should I do? No. I forgot how to copy. Now I know it. And basically we wanna compare whether how good is our model and how good would be the model if I just fit the data with a constant. So this is it behind the R squared value. How to put it in some formula? Well, there is a 1 minus, and now so what should happen? I want, let's take for example RMSE, or maybe we can just take the sum of squares. That's completely enough, because the rest of the terms would cancel out. So this one, if this one is small and this one is large, small, large, we are getting close to 1, and this is exactly how it works. So in the numerator we have this sum of squares of our model, of our prediction error. Yeah. And what we use in the denominator is k equal 1 yk, and well, how to fit this constant? Well, that's one of our lectures from before. Well, we can just take the average of the y's, average of our data points. Usually takes these values between 0 and 1, basically by construction. Sometimes it can happen that it can be negative. If it's negative for some reason, then pay attention. There was something wrong. There is some error with fitting the model. Yeah. If it would be negative, it would mean what? That our model, maybe it goes like this. Yeah. Maybe there was some error when doing the calculation of the model. Okay. Another, maybe close to visual, very nicely visualizable, is this parity plot, which you already which you have already seen. We started with it in the first lecture. The idea is, well, of course, these kind of plots, if we can do them, it's fine. What better assessment you can get? But well, they will work if we have one independent variable. Maybe if we have two independent variables, we can get a 3D plot. But if we have more of them, 10, it's already quite hard to see how the model performs. So for that, we can do this parity, or we can even call it correlation plot of the let's say our prediction versus our measurement. So if our prediction, our best model, we found the best model we found would be good, then what we would observe is basically this diagonal line, which means what? The value that our model would predict is exactly the value that our data observed. Of course, we cannot expect to be completely sitting on the line. There is still measurement noise, but this kind of situation, if our predictions versus our measured data lie next to this line, is quite okay, very much desirable. What are the possibilities of how this plot could look like in the different setting? No. One possibility, one probable situation would look like this. That of course you maybe have done everything right. Basically, what happens in this situation? If I predict something, but what I predicted has a corresponding measurement that is somewhere that is above this predicted value. But it at least has a good trend. Yeah, if I predict a larger number, then also the measurements correspond to the larger number. The problem that is signified by this plot is basically we either didn't select the correct model, which basically means we are missing some of the independent variables. Yeah, something is dependent on pressure, and we completely disregarded the pressure. So we are missing this information. That's for what our model suffers from. So missing regressor or missing input to the model. Another interesting situation is if this parity plot looks sort of okay-ish at some parts, and then it starts to somehow deviate. Yeah, so like a combination of these two situations. Again, might be similar reason, or the reason might also easily be that there is some nonlinear relationship that we didn't include in our assumptions. Some non-linear So what I recommend is when you are about to find the or train a model, don't rely just on RMSE. Check the R squared, check the parity plot. It's always different insight for different maybe candidate models. Okay. Another interesting point might be to calculate the confidence intervals. Confidence intervals of the parameters of a model. Why would it be reasonable? This maybe applies to the situation where we have a lot of data, so the confidence interval, the statistics basically works very well, but we can very easily get rid or even avoid the situations like this. If our octic model or whatever polynomial model would be, so to say, overfitted. There is one more parameter that just tries to fit the noise. Then also our confidence interval that will tell us basically the probability, the probable range of this value. It would basically contain 0, which is a good indication of this. That basically says with the same probability level, my model can live without the x cubed parameter, without the parameter p3. How to get to the confidence intervals? Well, we already know how to do this when we did the very simple linear regression, just for one slope. How to do this in general? It will again have to do with some matrices. Basically, we wanna find out some covariance matrix of parameters. If you recall, our covariance matrix of the data X looked something like this. We wanna do something similar. So we wanna do the average, this expected value we already used for. Now this is a. Does this work? Yes. Yeah, because this should be the matrix. So P times P transpose should give us matrix. So our vector P is MP times 1. Yeah, it's the column vector. Our vector P transpose is 1 by MP. So in developing this matrix, we should basically get information about each parameter and its standard deviation, its statistics. Yeah, so the matrix, this covariance matrix at the end would look very similarly to our covariance matrix for the data. What we had here, we had what was it? Variance of x1 covariance x1 x1, x2, and so on, and this matrix would look the same, would work the same way. Come here. We actually don't need this double index. Yeah, so we want to find how much the parameter P1 based on our measurements can spread its values, how uncertain this parameter is. Yeah. How to build this matrix should be pretty easy. We just take we know our parameters. That's our nice formula: x transpose x, x transpose y, and there is inverse. So basically, we can just plug this p into this p times p transpose. Would look messy in the beginning, but yeah, we'll work it out. So let's plug it in. Our VP is the expectation of, so our parameter P. Now we use the definition. X transpose x inverse x transpose y. Good. And now we need now we use the transpose of P. How would the transpose of P look like? Y transpose, yeah, we basically transpose all of these and we completely flip the order. Exactly. So Y transpose, then X, and then, well, we don't have anything to worry about because this matrix is symmetric. The covariance matrix is symmetric. Also, its inverse has to be symmetric. Okay, doesn't look very easy, but we just need to recall something that if what we just got here, the y transpose is nothing else than some covariance matrix of our data, which would mean, well, if our data are independent, what does it mean? That if I take one experiment and the second experiment will not be influenced by the first experiment. Yeah, the y is only the value of what I'm measuring, only depends on the independent variables, on the temperatures, pressures. Yeah, which basically means that, well, we will just have the variance of the basically measurement error. So how much our measured data are of their mean value. And if this measurement noise would be consistent, so would not change, would be constant, then basically our matrix would look just like this. Of course, it can be much bigger based on the number of data. Independent constant noise. But this means that we can actually simplify this expression and just use the variance of the measurement error and some identity matrix. So we can basically just plug this in, so our identity matrix would just do basically nothing, and we can plug the pull the variance of the measurement error out of this expectation. So that means, just say sigma square, and we have here already bunch of similar terms. They will simplify nicely. What do you think? What can we simplify here? With what can we do with it? So there is matrix A and there is matrix A inverse, right? So they just cancel out, or they become the unit matrix. So our final expression is just looking like x transpose x. Yeah. This is the variance of the parameters. Yes, but I mean, if we don't write it, this is already a matrix, yeah. So if I just write the square matrix here, it doesn't change anything, yeah. Okay. Yeah, it's different here, yeah. Here the one no, okay. Let me think. Should be there, right? I can do the should be there. How is it? Why would it disappear? Because basically, no, I don't know why. How would it disappear? So it should be there. Nah, I don't know. I'm missing something, but well, before we know anything more, I will check it and correct it maybe next time. The interesting observation is well, this matrix will tell us basically how uncertain are our parameter values. Of course, it should be directly corresponding to how large is our noise. Yeah, if our noise is large, our uncertainty in the parameters is big. The second one is even more interesting, because, well, the covariance matrix, the values of independent variables, that's our choice, that's our experiment. We are designing an experiment. We also already know that we shouldn't design experiments such that our independent data points are on the line. Actually, if they are on the line, there will be already problem with the inverse here, and also. There is a similar observation to what we made when we were doing the estimation of a constant. More measurements we take, the more this matrix would grow, and less, because there is the inverse, smaller will be our our error in the parameters. Good. Let's try to visualize it. If we have our basically, if we can very easily treat the parameter p again as a random number or random vector. We might have calculated maybe some estimated value of the parameters, and now we even have a covariance matrix. But well, we have seen this in our statistics whenever we describe something with these two parameters. One is vector now, and one is a matrix. Well, we can build some Gaussian probability distribution function. So let's say that we attempt this here. So the probability distribution function of our parameters now in the multi-dimensional settings. If you recall the scalar case, what did we have there? We had square root of 2 pi and sigma, yes, and we had the exponential function x minus x bar divided by 2 sigma square, yeah, something like this. This multidimensional variant will be very similar. We just need to take care about a few things. One thing is that our 2 pi has now exponent, and that's this normalization constant now in several variables. Our standard deviation, well, what was it in the scalar case? We just took a square root of the variance. We again take a square root of the variance, but we also need to get a single number. So we take a matrix square root and we take a determinant to actually. This will again be a scalar number because it's the probability density. That could work. And what happens with this one? Well, minus what? P minus P hat transpose VP inverse. Now there should be 1/2 somewhere. Minus 1/2 P minus P hat. Nothing else than just the vector matrix product, the brother of our scalar expression. There should be square here. Oops. Yeah. So this is a quadratic form. Well, instead of division with the covariance matrix, we just use the inverse. Okay, you suffered from this math, so it's time to show you some pictures. Let's see the pictures. Let's bring them somewhere up. Oh, where are we? Okay. So this is basically how our multi-dimensional PDF would look like. It's still this Gaussian curve, there is this sort of a bell, and if we, for example, look at this from the side of P1 and P2, it works quite nice because, well, let's say that we are looking at this from the side of P1. I usually use this. You take a torch, you shut down the lights, and you light the torch, and the shadow that this hill would project, well, it would look something like this. Yeah, there will be this Gaussian bell recovered. Basically, from this multi-dimensional picture, you can very easily get the one-dimensional information, and that's quite nice. That's not like it's granted or it's that obvious that we have this nice mathematics. Same would go for the parameter P2. Yeah, we can from this shine a light, and the shadow would give us this information about the P2. It's also not a coincidence that well, I visualized here this sort of a rings. Yeah, it's like a level sets. If I say, okay, I cut the PDF at the level of 0.002, then I basically have this ring that rules them all. How would it look in the?
Mm-hmm. We see like there are different steeps on one and the other side.
They are different.
Like
just repeat the word.
The steeps. Like
what is steep? Like slope?
Like the adjective. Jak po angielsku to powiedzieć?
Say it Slovak.
Że vlastně když zmniejšíš z jedné a z druhé strany, tak jsou různě ostré.
Strmé.
Strmé.
Okay, so the. From which one? From yes, I mean. You can. That's what you are saying is this curve. Yeah, I on purpose didn't plot a curve that would be like nicely symmetric. Of course, it exists, but on purpose I plot the curve where. Well, if we take now these rings and we just make them flat, do the contour plot, well, what can we observe? The spread of the P1 is much larger than the spread of the P2. So if this was the result of our regression, yeah, our regression gave us the point P hat, so the most probable value of the parameter, but also gave us the covariance matrix through which we actually got these level sets. Then this indicates how much uncertainty we have in which parameter, and it's clear that the uncertainty in parameter P1 is much larger. Basically, this thing we have here. Now I switch the colors. That wasn't good. So our uncertainty in P1 and uncertainty in P2. Yeah, it's obvious that our data and also our model told us more specific, more accurate information to estimate parameter P2 than the parameter P1. If you are asking yourself why there are these different rings and bands are actually these ellipses? Well, the reason is very simple. Like we did in the scalar case. In the scalar case, we took our quadratic form of this exponent. So the quadratic form, we took the x squared and said even if we have more x, even if we have sum of x squared, then this would obey the chi-square distribution. The similar thing we can do here, and we can take our P minus P hat transpose VP inverse and say that this is going to be distributed as a chi-square distribution with the np number of parameters. And how to get this ellipse? I think you either tried plotting an ellipse in one of the exercises, or you will do it today. So if we now take the quantile of the chi-square distribution, this is what we already done when we were trying to find the confidence interval for the estimation of a constant. Then basically this is nothing else than the equation of an ellipse. Probably I will get to it next time, how to plot this, because yeah, we have 15 minutes and probably it won't be enough. Yeah, but believe me, this is an equivalent of the of saying p1 square plus p2 square is equal to r square. That would be just the circle, right? Like x squared plus y squared is equal r squared. That's an equation of a circle. And now we do what? Now we do its matrix variant, and this guy here, where I forgot to put the -1, would serve would have its purpose. It's hard to say now. Mm-hmm. Yeah. It basically goes into this. Yeah, if you recall the high school ellipse, the high school ellipse looked like this. Yes, where we had the A was the length of one semi-axis, B was the length of another semi-axis, so they will be hidden in this matrix. Basically, they will be nothing else than the radii of the confidence intervals. But this matrix is also tilted, or this ellipse is also kinda rotated. So that's what we can get from the other elements from this matrix. Okay, let's see whether I forgot something important. Of course, with the best indication, if we recover our confidence interval, if the confidence interval contains 0, then this is a warning sign. Yeah, let's say that your regression ends up with the confidence interval, let's say -1, -1, 2. yeah, whatever 95% confidence interval. This is a raised hand or raised warning sign, red alert. Well, all the values between -1 and 2 are 95% probable. So also is the 0. So it's you should start thinking, can my model live without this parameter? Because obviously, well, it can be that this parameter is either not observable, yeah, linear dependence, or our data do not reveal enough of this parameter, or basically this parameter is bringing to the model some variable that has no correlation, no causal effect, nothing with the variable in question. Okay. If this is sort of clear, I wanna maybe just briefly mention at the end, with the help of some pictures, some component, some interesting method that pops up very frequently in the data analysis. Basically, PCA is something the whole world knows and uses. Is one of the first methods where, let's imagine a situation. Let's do it by example. Let's imagine this sort of a situation. We are now not dealing with any distillation column, anything. We are trying to process some images, and we have different images. What is it? 10 times 10, so 100 images. By the way, this is Steven Tyler here, George Bush, another George Bush. Maybe you can spot somebody else famous, Robbie Williams. Yeah. And so we have 100 data points. Oops. Yeah, okay. We have 100 data points. And well, how many variables do we have? How many if we wanna encode this image, how this image is encoded?
Resolution by pixels?
Yes. Okay. So let's say they are, I don't know, 400 pixels each. There are more, but yeah. So if we have 400 pixels, each pixel.
400 squared per one picture. Probably.
Yeah, but what does it mean, a pixel? So it will be like they are black and white images. So they the value, let's say every point in one picture. Yeah, I cannot zoom more. Every point in on one picture. This is too much zoomed in. Every point on a picture has a value between, let's say, 0 and 1. 0 means black, 1 means white. Yeah. So we actually have 100 data points, maybe, okay, let's say thousands. Yeah, let's just do it in order. Maybe we have 10,000 variables. So our matrix X actually lives in a world we have only 100 observations, and we have 10,000 different values that can change. Yeah, this is a different situation than, for example, you've seen in the exercises like the distillation column. We have maybe 20 different sensors, and we can and we have 1,000 times gathered the value from these sensors. This might become a problem. Let's say we want to do some sort of a prediction model, which means how would the prediction model look like? We have one parameter per one pixel. So we have one param P1, we have P2, until we have P 10,000 times X 10,000. So we want to learn 10,000 parameters, but well, just out of 100 data points, that wouldn't work, yeah, because the simple situation, if I wanna just learn one line, I need 2 points. Yeah, I have 2 parameters. I need at least 2 points. Now I have 10,000 parameters, so 10,000 lines. I need at least 10,000 data points. So what to do? This is where the principal component analysis comes in, and the principal component analysis is a technique which will let's put it like this. Okay, that wouldn't work. It will just try to observe and do some statistics, and so the principal component analysis was run here, and it constructed 2, 4, 6, 36 eigenfaces. So these are the most probable combinations, most probable but also independent combinations of the pixels given the data set, given these 100 images. Yeah. So now we only have this is basically saying yeah, you can see that this first image here, yeah, it's just saying it's quite probable, quite likely that many of the pixels are the same color. It doesn't say which exact color they are. It's just they share almost the same color. Basically, this one is trying to say, well, what is the background color on these images? And these guys here now become our, it's kind of new, it's new variables x1, x2 until x36, and our new prediction model can then, maybe let's call them x tilde. Our prediction model based on this can now just very easily live with these 36 parameters. So not 100, sorry, what was it? 10,000, not the 10,000 pixels information, but only 36 combinations. And well, here you can see how the images were reconstructed back. Of course, this Steven Tyler is visible here with his mouth full of teeth. There was the George Bush. Don't know whether you can recognize it from the beamer. What can you say? It's maybe not that easy to now recognize. Yeah, it's definitely an approximation. Yeah. Yeah, here the people are much more recognizable. But for example, if you are just living in this data set and you wanna tell, your system wants to tell Steven Tyler and George Bush apart, this is enough. And we got something working. We didn't need to fit 10,000 parameters where these parameters would be, most of them would have a 0 confidence interval. Yeah, so this is the sketchy visualization of the principal component analysis. The math is relatively easy. I can show you next time. Any questions to this? Okay.